Your GPU can still have compute available but refuse to run another LLM request. This happens when KV cache has filled available GPU memory. In this video, I will explain why KV cache grows with every active sequence, why this limit concurrency, and how paged attention helps Inference engine manage this memory efficiently. Here, compute utilization is around 60%, so the GPU still has compute headroom. But the memory available for KV cache is already full. The scheduler cannot admit another sequence because there is no memory to store its state. The model weights are already loaded on the GPU and shared by all the requests using that model replica. Each active sequence also keeps its own runtime state, and part of that state is the KV cache. The cache grows with the tokens in the prompt and with every token generated in the response. To understand why it consumes so much memory, let us first look at why it exists. Suppose the model receives a prompt with 500 tokens. During prefill, those tokens pass through the transformer layers. Each transformer layer has one or more attention layer. Inside each attention layer, model computes key value tensors for the prompt tokens. After prefill, the model produces the first output token. That token is then passed back through the model to generate the next one. During this decode step, the attention layer needs information from the existing context. The model may use information from any of the earlier tokens, not only the most recent generated token. Without a cache, the model would need to process the earlier tokens again during every decode step to reconstruct their keys and values. So when a token processed for the first time, its keys and values tensors are stored in the KV cache. Later, decode step read those stored tensors instead of recomputing them. That stored state is the KV cache. The amount of memory depends on several parts of the model. Number of tokens, transformer layer, KV heads, head dimension, 2 denotes the key and value, and bytes is the precision of the data. The exact amount varies across the model architecture, but the serving behavior is the same. Longer sequences holds more KV memory, and every active sequence has its own cache. This is why request count does not describe the workload properly, because 10 active requests with 1000 tokens each are very different from 10 active requests with 30,000 tokens each. Now the engine needs to allocate memory for those growing caches. A simple approach is to give every sequence one contiguous region of GPU memory. The problem is that engine does not know the final sequence length when the request starts. It may know the maximum allowed length, but it does not know whether the model will generate 100 tokens or 2000 tokens. Suppose the engine reserves a space for 2000 tokens, but the response finishes after 120 token. Most of the region was never used, but it remained unavailable to other sequences while the request was active. The engine could reserve a smaller region initially, but then the sequence may outgrow that allocation and need a larger contiguous region. There are another problems when requests finish. Requests have different lengths and complete at different times. When their memory is released, gap appears between the allocations that are still active. The GPU may have enough free memory in total, but the free space can be split across several smaller regions. A new sequence that needs one large contiguous region may still not fit. So the engine loses usable memory in two ways: unused reserved capacity and free memory divided across fragments. Continuous batching makes this allocation pattern common because sequences are entering, growing, and leaving. The engine needs a way to grow the KV cache without reserving one large continuous region for every sequence. This is what paged attention does. It divides KV cache memory into fixed size blocks and assign more blocks only as sequence grows. From the sequence point of view, the cache is still ordered. It has logical blocks 0, block 1, block 2, and so on. Those logical blocks do not need to be adjacent in physical GPU memory. One block can be stored here, another somewhere else, and the next one can use any available free location. A block table stores the mapping between the sequential logical blocks and their physical locations. When the attention kernel reads the KV cache, it uses that mapping to find the correct blocks. This is similar to virtual memory in an operating system. The sequence sees an ordered logical view while the runtime maps it to physical blocks in GPU memory. When the sequence needs more capacity, the block manager assigns another free block. When the sequence finishes, its block return to the free pool and can be reused by another request. There may still be some unused space in the final block if the sequence finishes before filling it, but that waste is limited to be part of one block. Paged attention does not reduce the amount of KV data required for each token. The model still needs the same key and value tensors. It reduces the memory lost to over reservation and fragmentation. There are some overhead because the runtime has to maintain block table, assign and release blocks, and read the cache through that mapping. Inference engines use specialized kernels and block managers to handle this efficiently, and even with paged attention, long sequence or enough active sequences will still fill the GPU. Paged attention helps the inference engine use the available memory more efficiently, but the underlying memory limits remains the same. When an inference engine stops admitting the request, GPU compute utilization alone does not give the complete picture. You also need to look at the KV cache utilization, resident tokens, active sequences, prompt length distribution, and output length distribution. Long context requests affect the system throughout the full generation. Their KV cache remains allocated while the sequence is active, and it continues growing as more tokens are produced. Continuous batching decides which sequence run during the next generation step. KV cache capacity limits how many sequences can remain active. Paged attention reduces the memory lost while managing those caches. The next scheduling problem is how the inference engine mixes the new requests that need prefill with the existing requests that are already decoding. Both create different kind of work, both need GPU, but the scheduling policy affect time to first token, inter token latency, and throughput. See you in the next one.